Good morning. How are you?
Good morning.
I love that look, Cassie. What does that mean? Are you doing great?
No.
No,
Here.
you're here. Well, here is part. It's half the battle, right? See if we can make it a little more lively. Okay, a few things. I have to leave early because I'm taking my sister to the hospital for surgery this morning, and so class is going to stop probably around 9ish on the dot. If I'm not done by 9ish, you need to kick me out. You got that, Cassie?
Yes, sir.
Okay, thank you. Also this week, there's the Black History event. You'll get your extra credit points. I'm a little slowish getting everything done. I spent the weekend enjoying myself instead of working hard on the thing. And I'm currently having some issues with the canvas shell. I can't make any adjustments. It's not saving anything that I'm doing right now. So I'm putting in a ticket. I just put in a ticket this morning for it to figure out what's going on. So somehow I managed to either lock myself out or something. So, but I should have that fixed by this evening. So you'll have a simulation lab to do this week if I could get it adjusted. If not, I'll give you enough time to actually get it done. And then on Wednesday, you guys will be building your spectrometers and then using those with the glow sticks. You guys should have a total of, there's a packet that's already open that has 3 glow sticks in it. And then there's a packet that is multiple colors. So you're going to be using those 2 packets, okay, with your spectrometer. In addition to that, you should also have alligator clips and LEDs. If I remember correctly, you should have 6 LEDs and 1 9-volt battery and the 9-volt battery cap or the. Okay, so you're going to put your alligator clips onto the wires on your 9-volt battery cap, and then you're going to put the alligator clips on your LEDs. Okay, you should also have a odometer. Yeah.
Yes.
Yeah. Okay. So those are the tools that you're going to be needing for the lab on Wednesday, because again, you're going to be using your spectrometer, the one that you're building with the black paper, and the diffraction slide to actually look at the different spectra of light. Okay, and that's with the LEDs and then also with the glow sticks. And so it's going to be crucial that you guys take a picture, and I'm going to hopefully, if I can get it to work, show you a way that you guys can calculate the intensity that is being performed. But it's important that you guys keep the settings of your photos exactly the same. You can't change your settings, okay? Any questions, Selena?
So it's, oh, wait, sorry.
Oh, you can go first. I don't mind.
Oh, so everything's gonna be in the lab box, correct, Dr. Henry?
Yeah, it should be in a lab box. If you have anything missing, let me know. And I'll try to get it out to you. I'm going to be out and about this week anyway, so I can drop it off at different locations. I'll be everywhere, put it like that.
Okay, and then today we don't have like the lab meeting that we have to go at 7 p.m.
Nope, you will have, hopefully I will get the issue with the portal fixed, the Canvas portal, so that I can make those changes. Yeah, so hopefully I'll get that done today. They'll come and respond to me today so that I can get that fixed to figure out what the problem is.
Okay.
And then, yeah, so all it is a simulation.
Got it.
I'm just hoping that it wasn't the same simulation that I gave you last semester.
We didn't, okay, that was my other question. I remember last week you said you were gonna post a lab simulation?
Yeah, I didn't post it last week.
Okay.
Yeah, I was saving it for this.
Okay.
Okay.
Dr. Henry, you said we can go to your office hours for makeup lab?
Yes. If
Okay.
you need to make up the lab, you can go to my office hours.
Okay.
And then
I'm
also,
gonna need 2 for Wednesday.
yeah, also we can also make arrangements because I have a bio lab but we can set you aside to go into that bio lab as well.
Okay.
So that, you know.
I'll email you.
Morning. Okay, so any other questions?
Dr. Henry. I think I think I remember sending you an email that I was missing the alligator clips and I think the filter paper or something. Yeah, the filter paper.
Okay. So yeah, you did send me that information. I will drop that off for you this week. So you'll get it before Wednesday.
So the spectrometer lab we're gonna do on Wednesday, right? Or
Yeah, on Wednesday.
okay. Thank you.
Okay. Ms. Garcia. I don't know. I don't know of a student. There we go. Hi, Sadie. How are you? Okay, so are there any other questions?
No, I think we're good.
Okay. Okay, Abby, I am almost finished with your recommendation. I should be finishing that up tonight, so
No worries.
it'll get done.
Thank you, Dr. Henry.
No problem. Okay, so I heard that you guys did electron configuration.
Yes.
Excellent. And I heard it was a great job.
Yeah.
It's good. That's what we want to hear. Okay, so now I'm going to talk to you guys about your quantum numbers, right? So let me start sharing. Okay. So there are going to be 4 quantum numbers that are associated with each and every electron in an atom. Okay. And it's kind of like the way I like looking at it, thinking of it, is like an address. So each electron has an address that's associated with it. We have to use 4 different quantum numbers. Okay. So I'm going to talk to you about each of those different quantum numbers. And we've got to think about it in terms of what you guys learned. So we talked about the energy levels. Okay? You guys familiar with that? That was the first thing that we talked about.
Yeah.
Then we start talking about the angular momentum, right? Then we talked about the radial momentum. Okay, so, and then the last thing that we're going to be talking about is going to be our spin. Okay, so those are all of the different aspects of the electron. So it kind of tells us where the electron is roughly located, which way it's possibly spinning, you know, so there's information that is provided in those numbers. And so it's a nice quick way of understanding the process without having to do all the calculations all the time. You guys get that? You with me so far? Although I know you guys love doing calculations. I heard that you guys are like on fire with the calculations. Is that true?
Yeah.
Good. I like hearing that. So one thing we always want to remember, we're talking about quantizing, or basically we're talking about those specific, you know, levels of energy that are associated with quantization. Okay. So when we're talking about quantization, we're talking about like those specific levels. Okay. So, and then again, specific locations and specific addresses. Okay. Or I should say ballpark, not necessarily specific, because we haven't gotten that good yet. Okay. So we talked about the different energy levels. And so we term those energy levels in terms of n values, in 1, in 2, in 3, because we can use those integers, because basically the equation is essentially the same. So that bundle of energy can just be multiplied by the level that it's at, or that integer that it's at, to get the energy that's associated with it. So because of that in 1, that in 2, that in 3, right? That's going to be our very first quantum number, right? That's going to be our principal quantum number. Okay, that also represents the levels that we see on the periodic table that are our periods. Period 1, your energy level 1, it represents N1. Period 2, that represents N2. So are you guys with me?
Yeah.
Okay, good. And I'll show you a periodic table here in a second. Okay, so again, Bohr was the one that kind of figured this out, and it's initially based upon the Bohr atom, but that was the first part. He only worked on that first quantum number. He didn't take all of the other quantum numbers into consideration. And so that is the complexity of quantum mechanics or quantum energy, is the fact that you can't only take that principal number into consideration, or that energy level, because that's what the principal number represents. We have to take into consideration angular momentum, spin, all of those things to sit there and get a true representation of what's going on with that single electron. Okay? Are you with me?
Yep.
Okay, so this is just basically showing you. Okay, so here's our nuclei. These are the different energy levels, right? And then it goes on to N4, N5, N6, N7. So if you guys remember on the periodic table, how high
What?
that N value on the periodic table, what is the maximum number that you guys see on the
7?
periodic table? 7, right? So we go up to N7. Okay, so here's a question for you. Is there a possibility of going higher than N7?
Yes.
Yes, yes, it is. Because in theory, it goes to infinity, because there are things that we just don't know yet. There could be an atom that has more than the number of electrons that are currently shown on the periodic table, but we just haven't discovered it yet. Our technology is limited, or we're just not able to make it stable enough in time. We haven't figured things out, so we have time to figure it out. So we want to make sure that we understand that those energy levels can go up to infinity, okay? So we can expand beyond that 7th level, right? So if you guys happen to discover the next atom that is beyond the periodic table, we know that there's a possibility that it exists, okay? So if we sit there, we're thinking about this, right? Because we're able to go on to that next energy level, we're able to sit there and think beyond that, right? So science, in a sense, isn't limited. We have the ability, we left the room open for the possibility of there being other atoms that we just are not familiar with, or just not able to comprehend, or just not able to make or find, okay? Because could you imagine? The periodic table before was probably consisting of only those few things that we see, with our eyes, coal, right? Initially, we may have gotten a little bit of a sulfur, So, but we've expanded that periodic table from that point. Are you with me? Is it making sense?
Yep.
Okay. Okay, so we talked about the first energy level. The first principal number, and that's just the energy levels. Okay, so we know that that has to be an integer. It can't be a fraction or anything like that. It always has to be from 1 to infinity. Okay, potentially. Okay, so the next energy level represents the orbit. Now, when we're talking about the orbit, you remember the S, the P. Did you guys talk about that with Jessica?
Yeah.
Yeah.
So the S orbital, the P orbital, the what?
D and F.
The D, the F. And then there's a possibility of going on beyond that, because we know that the energy levels, right, extend beyond that, right? And I'm going to explain to you how the atomic orbital affects the energy level affects the atomic orbital here mathematically, or numerically, I should say, not mathematically. But in this concept, right? So the angular, or the atomic orbitals, the S, the P, so then that allows us to sit there and talk about that 3-dimensional aspect. Okay. So are you with me so far? Okay, so good. So specifically, the atomic orbital actually is the angular momentum orbital, right? We call it L. So N represented the principal number or the energy levels. L is going to represent the angular momentum. So that's going to be our S, our P, our D, our F. Okay, so if we have L0, so the way it works is, you look at this, you guys see, right on my board. L being the angular momentum quantum number, that's going to go from 0 to n minus 1, right? So if L is, I mean, if n is 1, then what is L? Selena?
0.
0, right? Because we know if we put 1 for n, it's 0. Okay, so L being 0 is going to be equal to the s orbital. Okay, if L is, if n is 2, then what is L?
1.
Okay, if n is 7, then what is 1? I mean, what is L?
3. Would that be F?
So if n is 7, what is L? What is the maximum that L can be?
3.
6, because
Oh,
remember 7 minus 1. Okay. Are you with me?
Yeah.
Okay. So, so when we talk about those energy levels, we could sit there and use that as forms of calculations. So are you kind of are getting it, or are we just kind of like, nah, we don't got this?
do you always do n minus 1? That's where I'm confused, because I was just, the way Jessica described it last week was, it was just SPD and F, the 0 through 3.
Okay, but see, that's why you guys were, that's the intro, right? So we're going to expand it. I don't want you guys to limit yourself. Okay? So you're always going to do n minus 1. That is the maximum value that you could have. It can go up to n minus 1. L can have a value. If it's 7, it's n minus, well, if it's 7, it would go from L is equal to 0 all the way up to 6. That is the maximum that we can get. Now, we will talk specifically what each of the ones mean. 0 is going to be the s orbital. 1 is going to be the p orbital. We're going to talk about that here in a second. Promise.
So then you're going to have multiple values for L then.
There is, yes, because each one, remember, it represents, L is just one of the principal numbers. I mean, or
Okay.
one of the quantum numbers that we're looking at, right? And so
Okay.
you're basically using it as an address. You know, where do you live at?
2850
2850 what? What's
South Vintage.
South Vintage? So South Vintage is the street you live on. Your specific address, because if I just said, oh, Cassie lives on South Vintage, and I tell everybody, okay, we're going to go to Cassie's house, we're going to South Vintage. How are they going to be able to find you? Aren't there a lot of houses on South Vintage?
Mm-hmm.
Right. So that's the same way with the
Okay.
electrons. And in an atom, no two electrons will have the same address. No two electrons will have the same quantum number. So that address is those quantum numbers. Do you get it?
Mm-hmm.
And so that's why it's important that we make that distinction right now. And then we also need to give it some flexibility. So because we know we're limited, we're not perfect. You know, as much as I try to be perfect, and I'm perfect 99.9% of the time, I know that 1% that I'm not. Okay. Okay, are we good so far?
You said no electron shares an orbital.
No, I said no two electrons will have the same set of quantum numbers or the same address. Right? That's kind of like Cassie. Let's say, Cassie, what is your neighbor's name?
Mario.
Mario. Cassie and Mario don't live at the same house, right? And if I'm delivering my mail to Mario, to Cassie's house, right? Mario's gonna get a little pissed off after a while that he always have to go to Cassie to go get his mail. You know, he got his big tax return and stuff like that. And Cassie says, "Oh, this is nice," you know. So, you guys, you see what I'm saying?
Mhm.
Okay, so let's go on with these orbitals, right? Okay, so these orbitals, this L, they represent those subshells like we were sitting there talking about, the S, the P, the D, the F. So, come on. So L0, that represents our S orbital. L equal 1, that would be the P. L equal 2, that would be the D. L equal 3, that would be F. L could be 4, that would be G. L equal 5, that will be H. But the thing is that right now we're limited by what we know and what we're able to see. We're limited by our human limitations, right? We haven't been able to make a stable structure where we're actually in the G level. We made attempts. We made a lot of explosions making those attempts, but we've not been able to find anything stable yet. So that doesn't mean that it doesn't exist. It just means that we're incapable of doing it right now. You guys, are you with me?
And that's just because of technology. That's not because of like we have theories supporting it type of thing.
It is. So we have theories supporting that they exist, right?
Okay,
But we're
you
limited by
can't
technology.
test it. Okay.
Yeah, it's hard to test because you get into the realm of explosions, right? So you're putting protons and neutrons together in a fashion that may not necessarily be stable. You're making things that are often unstable. So they set off, as soon as you get them started, they'll set off a little mini explosion in a lot of cases, sometimes major explosions.
Okay.
Because we haven't found the ability to get those stable structures made. Okay, so that deals a lot with that nuclear energy that will be talked about at the very end briefly. But you know, it's that concept where, like, if you start looking at some of the periodic table, there'll be one periodic table that will give you one number for the number of neutrons. It'll give you different mass. You'll have an element that have two different mass numbers. I'm trying to remember the one specifically because under one circumstances, we had a group that claimed it was stable under this circumstance, and then we had a group that said it was stable under this circumstance, right? And so in theory, how you should resolve that is say they're possible isotopes of each other. Both of them are stable, right? But only one says that it was stable under, there's a minimal stability requirement that it has to stay stable within, like, I think 2 microseconds, something like that. And then we'll say, okay, that's an element, right? So there's some discrepancy about the time that was there. So there's 2 different values that are listed, right? So if you look at one periodic table, it will give you one value. If you look at another periodic table, it'll give you a different value. Okay. So that lets us know that that whole concept of stability, right, plays a huge part in this process. But we want that possibility of knowing that there are others. So if I had L5, then that would be the H. If I had L6, that would be the I. Do you guys see the pattern?
Mm-hmm.
Like once you get to that F, it just follows it, G, H, I. I don't know what happens when we get all the way up to, because I guess P would be that letter that would come first. No, S, then P, right? So S, P. I don't know what happens after that. It's like, no. Are you with me?
Yeah.
Okay. So that's the angular. So tell me, what is the first quantum number that's represented by N? N, and it
It's the
represents what?
Energy.
Yeah, so we know it's the energy. We call that what quantum number?
Principal quantum number.
Principal. Okay, so then the second quantum number that's represented is the angular momentum quantum number. That's this guy. Okay. So the next quantum number that we're going to be looking at, because we talked about the angular momentum. So that's going to be our radial nodes. So those points, remember what the nodes are? Those points that hold it together, right? So those radial nodes. Okay. So in the case of your radial nodes, that's going to be our next set of quantum numbers. So radial nodes are basically going to go from the way that we would calculate the number of radial nodes that we have is going to be n minus L minus 1. Okay, so okay, so here clear. Okay, so for 1s, n is going to equal 1, L is going to equal 0. Right? So the number of radial nodes is going to be 1 minus 0 minus 1. So there are going to be 0 nodes associated with it. Are you with me? For 2s, so it's going to be n is equal to 2, L minus L, which is 0, minus 1. It's going to equal 1. So then we're able to sit there and calculate those nodes. Now, what does those nodes mean to us, right? Well, let's take a look. Okay. So those nodes basically tells us probability of where things are going to be at, where we're capturing it. So its nodes are like the ends of where the event's at. Okay. So in theory, they say the first one, oh, there's no nodes. Okay, here we have this guy here, 1. This here would represent that 1 node. So that region where it's going to be at. Okay. So no nodes, 1 node, 2 nodes, 1, 2. No nodes, 1 node, 2 nodes. You guys get it?
Yeah.
Okay. So it's going to represent that space between those s orbitals, right? So that's the 1s. There's no space. Okay. Between the 1s and 2s, oh, there's space, 1 node. 1s, 2s, 3s, 1s, 2s, 3s, 1, 2 nodes. Okay. Okay, so let's talk about the shapes of the s orbital, the p orbital, the e orbital, and the f orbital. Okay, so the s orbital is always going to be a spherical shape. It's a circle, right? A ball, and be shaped just like a ball. Okay, the p orbital is going to be dumbbell shaped. So you guys know what a dumbbell looks like, or I like to look at it like a yeast, a budding yeast. You guys ever seen a budding yeast under a microscope? Now, the D and the F, they're a little more complicated. And the important thing is that, remember, these are 3-dimensional structures. This orbit that they're taking on is a 3-dimensional structure.
So a subshell and an orbital is the same thing.
Yeah, we have a bad habit of using them for the same. Really, you should say subshell, because we will talk about specific orbitals within a subshell. Yeah. And you'll notice it's not the same, because I looked at the text, the actual text, and we have a really bad habit of interchanging them. And so it brings a little bit of confusion. So you want to kind of clarify. Sometimes we'll give you clarification, right? So they say D and the F orbitals in that case. So they're making sure they're saying the D and the F rather than just saying orbitals, because you will have an orbital within the D and the F. Do you understand what I'm saying?
So the subshell is within the orbital, or the orbitals within the subshell?
So it's subshell, and then the orbitals are within the subshell.
Okay.
Okay. So let me explain to you that in a little more detail here by showing you the different orbitals. So the S is real simple. It has a single orbital, right? It's all sphere, 1 here. The P has 3 different orbitals in the subshell, the P subshell. you have the, what we call px, or sometimes you'll see it written as p minus 1. This guy here, this guy is p0. This guy here is p1, right? So remind me, what is the maximum value that you can have for L if you're in, let's say, 2, because 2 is where we first get our P, right? So we have 2 n is equal to 2. What is the maximum that L can be?
1.
So L can be 1, right? Okay, so we know that the maximum value that L can be is 1 in that case. So we can have 0 or 1. Okay, so the next value that we have, so that's our angular momentum. The next one is called the magnetic quantum number, and that's called, often you'll see written as ML. Now, ML means basically we have the value that goes from L minus L to plus L. That's a minus L, okay? And I'll show you what that, so what that means now is that we have values that are going from minus L. So if we're talking about the p orbital is what again? What value is p orbital? For L?
1.
1, okay? So if we're going L has the possibility of being, we're going from minus L to L. What are the values of our ML?
-1 to 1.
So it's -1 to 1. Or specifically, it's -1, 0, 1. Are you with me?
Dr. Henry, I have a quick question.
Mhm.
Where do you get the 0 in the L?
Because it's L is equal from 0 to n minus 1. So it can be all of those values. So your L value can go from 0 to n minus 1. So for instance, if we were talking about n equals 1, right? So if we have at a quantum number of 1, what value would n equal? I mean, what value would L equal?
0?
0. Okay, so we know that L represents the subshells. So a 0 subshell is what?
S?
S. Okay, so let me do this one. Okay, so at energy level 1, what different subshells do we have?
Just S.
We just have S, right? So does that make sense?
So is it always going to be within that range from like 0 to n minus 1 in all cases?
Yes, so it's going to be, so you have the possibility of having electrons that are from 0 to n minus 1. Yeah, for all possibilities.
Okay.
Okay.
Yep.
So are you with me? So that's why I'm saying you've got to, so we have a tendency, because I see this as a cell phone, right? And I know that I can use a cell phone to make phone calls. Is that true?
Yes.
Okay, but I see it's a cell phone. And I know it exists because I know I can call you if I wanted to, or I can call Kayla, or I can call Cassie, right?
Yeah.
Right. So in the old days, right, we had the phones that were connected to wires and stuff like that. And if I showed somebody in the old days that this is a cell phone, I can be anywhere and I can make that call as long as my battery is charged, right? I'm good to go. They would have said, you're full of shit, right? There's no way you can do it. Because why?
Because technology.
Because of technology, right? Well, because of technology, we're able to do that. Also, because of the fact that somebody recognized that we have limitations. We've set these limitations, right? So as scientists, we've got to get you guys out of the habit of setting those limitations and looking beyond those, right? And so we also need to set up science so that it's able to expand beyond that. So when Selena's saying, well, so does that mean that it can go to n-1? Yeah, it means it goes to n-1. We're setting up that possibility that n could be greater than just 7, because doesn't n only go to 7 on our periodic table?
Yeah.
So in a sense, we're setting guidelines based upon data that we've observed. So we know that we can at least go up to 7, but we also set the possibility that we can expand beyond that. Are you with me?
Yeah.
You're giggling, Cassie. Why are you giggling?
All I heard right now is Pirates of the Caribbean. They're more like guidelines anyway. That's all I heard.
Exactly. That's exactly it.
I was
You know,
just thinking like
Pirates had it right.
applying the principle of like
Yep.
sorry.
Okay. So let's go back to our image. So does that kind of explain it? Can you see the connection, right? So let's say, for instance, now we're talking about n equals 2. So n equals 2 can be 0 and L. Okay, so what does the 0 represent? Again, which orbital? Which subshell?
S.
The S. Okay, what does the 1 represent?
P.
The P. So what do we have in the second energy level?
S and P.
We have S and we have P, right? So are you guys starting to see the magic?
When you did it like that, it was like a light bulb.
Didn't I just blow your mind?
Yeah,
Right?
a little bit.
So let's do the third energy level, right? So we have n equals 3. L could be what?
0, 1, 2.
0, 1, 2. Okay. So we know that means 0 is what? S again?
Yeah.
1 is,
P.
and then 2 is,
D.
okay. So third energy level, we have S, we have P, and guess what? We start here at the 3D,
Yeah.
right? Yeah. Mind blowing.
Yeah.
Okay. With me so far?
Yep.
Good.
Dr. Henry.
Yep.
20-minute warning.
Thank you. Thank you. I need that
I know.
because I get so excited, and I lose track of time. Okay. So let me show you about the S, the P, the D, right? So we also talked about the angular quantum number. So and that was L going from minus L to L. Parentheses there. All right. So L again representing the P, I mean not the subshells. So if L is 0, then L can go from the angular momentum can go from what? ML is going to be what?
Just 0.
Just 0. So if L is equal to 1, then what is the ML? What can ML be?
-1, 0, and 1.
Okay. So remind me, L equal 1 is which orbital? S, P, or D?
P.
It's P, right? So this here represents P minus 1. This here represents P0. This represents P1. All of those are P orbitals, right? Because how many electrons can the P shell have in it? Each orbital can, that's right, 6. Each orbital contains 2 electrons, or can contain 2 electrons. So you could have 2 in the P minus 1, 2 in the P0, or 2 in the 1. This here is another way that we depict it based upon the axis that those orbitals reside in. So this guy resides in the x-axis, this guy would reside in the z-axis, this guy would reside in the y-axis. Okay, all of those orbitals exist, they're overlapping with each other, and they don't interfere with each other. Are you with me?
Yeah.
You have that look, Cassie.
Sorry. Processing.
Okay, processing is good. So let's see, what if L is equal to 2? What does that represent?
E.
It represents D, right? So then ML is going to equal what?
-2, 1, -1, 0, 1, and 2.
How many orbitals are in the D subshell?
5.
1, 2, 3, 4, 5. Wow. 1, 2, 3, 4, 5. So here's your D minus 2. Here's your D minus 1. Here's your D0. Here's your D1. Here's your D2. Now, when we name them, we call this DXY because it's in the X and the Y three-dimensional space. We call this one DXZ because it's in the X and the Z three-dimensional space. This guy is called DZ2 because it's crazy. It's called cray-cray, you know? So, and then this guy is in the DYZ space. This guy is in the X2, Y2 space. So it avoids the Z entirely. It's just in the X, not in the X and Y, but it's in that open space between the X and the Y. You understand? This guy was actually on the X and the Y. This guy is in the open space between the X and the Y. So that's why they call it DX2 minus XY, because it's in that open space. So now you
Not
see all
fo-
the complexity.
Yeah.
You're not fully getting it?
No,
Okay, so like these
because all
guys
I'm
here,
all I'm seeing is like they all.
so I'm sorry, let me correct that. So this is XY because you're in the space between the X and the Y. This guy, space between the X and the Y, this guy is actually on the line rather than space. You see the distinction between this guy and this guy?
So what would you call that one if it's not on an axis? On one of the...
This one?
Yeah.
So since it's not on the axis, we call that one DXY. Since this guy
okay.
is actually on the axes, right? It's on the X and the Y axes, we call it DX squared minus Y squared. I know it's crazy, but it's just a nice way of letting us understand that they're 2 different orbitals, right? They exist both on the X and Y, but they're 2 different orbitals on that X and Y plane. Does that help? I mean, of course you have the height and the Z, but really the Z isn't changing in terms of the height. It's the X and Y that you're orbiting. You guys have that look.
I'm understanding it, but might need some practice. So.
Okay. So, but the major point is that there are 5 orbitals, right? 1, 2, 3, 4, 5. That is the major point. If you guys decide to go into quantum, you'll talk more about what specifically that dxy means mathematically. There's some mathematical aspects to that. Okay. Are you with me?
Yeah.
You ready to go to the F? What about the F?
7 orbitals.
7, right? 1, 2, 3, 4, 5, 6, 7. So we know that that's 3. L equals 3. So that's the F. And so ML equals -3, -2, -1, 0, 1, 2, 3. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Now, because these guys are cray-cray, they're like really complex, they just call that the F -3, the F -2, the F -1, 0. Okay. Now, they probably have specific X and Y components to it, but I don't know them because it wasn't taught when I was in school. And I'm old. So if you guys get into quantum, you can update my slide for me later on.
Sorry, Dr. Henry, can you hear me now?
I can hear you now.
Okay, so we're not going to need to get specifically into the axes, and we just need to understand that there's the different orbitals, meaning like the way that they are turning.
You may see, let me kind of clarify that.
Okay.
You need to be familiar with them, but you're not going to need to know them in depth. But you may see, okay, so we have the dx2 minus xy. How many electrons are in it?
Well, D has 10, right?
What D has 10, but how many are in specifically the dx2 minus xy? What is the most that it can hold?
2.
Because each one of these, that's 2, that's 4, that's 6, that's 8, 10. So D altogether, this is D altogether. This represents one orbital in the D. This is another 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 orbital. Each one of them can only hold at most how many?
2.
2. Okay. So here's the next thing I'm going to throw at you now, and then I'll repeat it later. The rule is that each orbital, before you can go on to the next subshell, has to have at least one electron. So it fill this guy up. It'll fill up this orbital before it fills up this orbital, in most cases. There are exceptions. And then you're going to ask me, do we need to know these exceptions? Right? Is that what the next question was going to be? Yes, you're going to have to know those exceptions. And I'll show you some methods of understanding and knowing those exceptions. Some of it makes sense. Some of it is just like fucking crazy. I'm not going to lie to you. It isn't. It's crazy. But it all has to do with energy levels. And there are other aspects that we just don't quite get because of the complexity of these orbitals. Okay? We can't see them visually. Can't imagine it visually. We have to rely on the energy levels that are being presented. Okay? So let's move on. So we've talked about which orbitals so far. I mean, which quantum numbers so far?
N, L, and ML.
N, L, and ML. Okay. Erase clear. Okay, so you guys are filling it. You're filling the whole issue. Okay, so now let me ask you some really hard stuff. So if we had a G orbital or a G subshell, how many orbitals would G have?
9.
That's right. And then what would your L value be?
4.
And what could your ML be?
-4 to 4.
-4 to 4. Okay, simple.
Yeah.
Okay. Okay, so let's move on. Okay, so the next thing that we want to talk about is degeneracy, right? Degeneracy is basically loss of, right? So remember when we were talking about the 2s, the 2p, and then we also talked about the 3d, right? The 3d is at another energy level, right? So technically it's at the 4 energy level. Did you guys see that in the periodic table?
Mm-hmm.
Okay. So in that context, when we start getting up to those other ones, we drop down that level or we go up that level, right? So that's partial that explanation is because of that. Okay. So and then the fact that we go from also that L value, right? That L value is going to be 1 less than the N value. Okay. So let's look at this, right? Okay. Here's our 1s in terms of energy. Then it goes to 2s. Then it goes to 2p. Then it goes to 3d. Then it goes to 3p. I'm sorry. So 1s, 2s, yes, 3s, not 3d. Then it goes, there it would go up to 3d. But if you notice, look here. Right here, this is energy, right? Who's higher in energy, 3d or 4s, based upon the graph?
3D.
3d is higher in energy, right? So we filled the 4s before we fill the 3d in terms of electrons. Are you with me?
Yeah.
Okay. So that is an example of degeneracy, right? Because otherwise it'll just go up the way it's supposed to, right? And you'll see this throughout it. And so when we get up to the G's and the H's and stuff like that, they'll also have that issue as well. So, and that also makes it a little more complicated. So we'll have to wait till we get to that point. Okay. Okay, good, good.
You have 5 minutes, Dr. Henry.
Okay, I'm wrapping them up right now. So we're on the last quantum number. So the last quantum number is the spin, right? So it represents a spin. Two spins, you could either have a plus a half or a minus a half. Okay. So that the spin represents the rotation of the electron. So they can't be spinning the same way, because if they're spinning the same way, they generate they would generate an energy pulse that would be additive rather than cancel each other out. The goal is to try to get them to spin so they kind of cancel each other out. So you spin one way and you spin one the other way. So then what you're going to have is your MS is going to equal plus a half, or it's going to equal minus a half, representing the spin at each way. Right? So here's plus a half, minus a half. Right? So they're spinning in different ways. Okay, so those values cancel each other out in terms of the magnetic field that's being generated, rather than amplifying. Are you with me?
Mm-hmm.
Okay, so 4 quantum numbers. Every electron in an atom is represented by 4 quantum numbers: the N, the L, the ML, and the MS. Okay, what are the quantum numbers again? What are they called? The first one, the N.
Principal quantum number.
The L.
Angular momentum.
Quantum number. The ML.
Magnetic.
Magnetic.
That's right, the magnetic quantum number. The MS.
Spin.
Okay, piece of cake?
Yeah.
Okay, so before we wrap up, let's see, 3 minutes. So before we wrap up, let's talk about Pauli's exclusion principle, right? Pauli basically says that no two electrons will have the same set of 4 quantum numbers. That's it, right? That's it. He says they can't be exactly the same because each electron have a different address. Every electron in an atom has a different address. You can't have them both at the same spot. Right? Sadie, you don't live where Cassie lives, do you?
No.
You guys don't have the same address. So if I send your mail to Cassie, are you going to get it?
No.
No. Okay. So that's exactly what's happening here. Each electron has its own address, right? It has those 4 unique quantum numbers for itself in a single atom. Okay. Piece of cake. So since we said that, we can also say that no more than 2 electrons can occupy the same orbit. So in other words, you can only have 2 electrons in the same orbit. One has to be spinning one way and one has to be spinning the other way. Make sense?
Yeah.
Okay. So this is the general summary of everything that we just talked about. And you guys have already done electron configuration. Then what we're going to do next, when we come back on Wednesday, we will actually go through one of those structures, and then I'll show you the plus and the ups and downs of the arrows and stuff. You guys can actually start using those energy levels for things, because that's going to be important here later on. Okay?
Sounds good.
Okay, so we'll break, and I will see you guys on Wednesday. I will see about trying to get that fixed as soon as I can. Hopefully, I think I got an email from them, so it may be something really stupid on my part. It usually is.
I emailed you about scheduling, Dr. Henry.
Okay, sounds good. But we'll make a schedule for you.
Okay.
Okay? Okay, I missed you guys. Oh, by the way, Selena, awesome job. I loved it. It was great. Can you do me a favor? Send me your address. So I
Yeah.
can send you. Yeah. Oh, did you already do that? I haven't checked my mail, to be honest.
No, I haven't done that yet.
Okay, so do that. And is there anybody else? And Abby,
Yeah.
you too. Send your address. Congratulations. You guys did a great job. I'm very pleased. You guys, I almost cried. You guys made me so, so proud. And
Okay.
mom rap.
Okay.
Didn't
So
get to
I'll
show
send you-
it.
I know. Don't worry.
Did you watch it?
I have Bruce send it to me. I have it in my shell now. I'm going to be watching it this weekend. I'm going to say, I told you, I'm going to put you on blast. Okay, so I need to let you guys go. I'm out the door. I'll see you guys later. Have a good day.